So okay, so let me start sharing the PPT. Okay, or let me first share the assignment 4. Yes. So is it visible? My screen? Uh, is it visible? My screen is visible?
Yes, sir.
Okay. So let me start, and if you face any problem in between, like voice is not coming or something, you can let me know. So this is the an assignment 4. It is mostly talked about the bridgeless PFC, totem pole PFC, and then some things related to DCM operation as well. So in assignment 4, the first problem was for totem pole PFC. What is the RMS current expressions for switch S1? We know that the switch S1, whatever is here, the switch S1, whatever is here, conducts for dt period in the dt TS period in the positive half cycle. So let me write down. It it conducts. So it actually we know that our S1 switch conducts for 1 minus d TS period during positive half cycle Vs greater than 0, and during D of TS period when SVS is less than 0, or you can say negative half cycle. So that is the reason why we have taken our expression, which is 1 by T, because we have it is in one half line cycle, because in another half line cycle it will repeat itself. So it goes from 0 to T by 2. It is there for dt period, in the positive half cycle and in the negative half cycle. So we have taken overall T, because okay, here we have totem pole PFC, so both the period half cycle it is slightly different. So that's why in positive half cycle it is 1 minus d portion of the switching cycle, that's why it is just 1 minus d of t is square, and then in the negative half cycle it is d of t dt of ts switching period duration when the switch S1 is conducting. So we have to take d of t and is square, and that everything will be under root 2. So the correct answer is answer B. Then comes the question number 2, where we have given that for bridgeless PFC converter fed from 50 Hz AC source having varying voltage, which is between 200 to 250 volt. That means here we have given that the AC input voltage is varying from 200 volt to 250 volt. So we have to see what will be the minimum value of duty ratio of switch S1 in positive half line cycle if this output voltage is kept at 425 volt. So similar to that problem we have done in the last assignment also, but for boost PFC case. So let us take how we can do this particular exercise. So in this exercise we will first take our bridgeless PFC, and we know that our input varies from 250 to 200 to 250 volt. So our if we see our duty ratio of S1 is, in positive half cycle S1 is turned on and turned off with the time for the time duration of dt of TS period. In negative half cycle it is completely off, because it's diode diode which is connected across S1, which is conducting. Similarly, on the other side, on the half bridge, on the second half bridge, it is the for S2 switch, it is 0 in positive half cycle, and it is the T duty ratio will be dt for negative half cycle. We know that our duty ratio varies with 1 minus modulus Vs peak sin omega t by V naught in this manner. So if we draw the duty ratio of S1, it will go like this. In positive half cycle, it is the same, well, it has the value same as that of d of t, which looks like this. And after that, in the negative half cycle, it is 0. So this is, if I try to write, this is positive half cycle, this is negative half cycle. Then again it's a positive half cycle, which will start in the next cycle. So as a result of which what we will see is that our minimum duty ratio achieves, we will achieve it at, it has period where our Vs peak. If I try to draw my Vs is going like this. So at the peak of the Vs, my duty ratio will be the minimum, and that we can, that is a point where my duty ratio will be the minimum. And we know that our duty ratio is nothing but, finally when we solve, what we will get is our duty ratio is nothing but 1 minus, the minimum value of duty ratio is 1 minus Vs peak V naught, because at omega t equal to 90 degree that we will achieve that. So what we will get is Vs peak. Now there are two voltages which are given, because voltages are varying between 200 volt and 250 volt. So as we increase this, so for we have to always take, since we have asked for the minimum value, we have to take the data for, 250 volt case, because that will give you the lowermost duty ratio. So that is the reason why we have taken for 250 volt Vs peak. Since it is given 250 volt, it is the RMS value, so we have to convert it into the peak value, and that we will get over here. This we will divide by V naught, which is given as 425, and finally what we will get is, we will get the duty ratio, which is minimum value of duty ratio, which is 0.168. Similarly, if you put it for 200 volt, it will be coming around 282 volt divided by 425 minus 1 plus 1. So it is 0.334 volt. Sorry, 0. So duty ratio, if I try to write duty ratio minimum value for 200 volt, it is 0.334. And if we see for duty ratio for 250 volt, it is a lowermost, that's why the value lowermost duty ratio we have to take, and that is the value we have to take. So that is the range which is given, and the correct value is 0.168. So that was the second problem. Which is the second problem? Yeah, that is the second problem. Third problem, our totem pole PFC is a single phase power factor correction converter, and it is having unity power factor operation. So again, when you do the power balance, what we will see is that on the output capacitor we have the second line harmonic component of voltage ripple. So that is why answer D is correct, which is second line harmonic component of component which will be there on the voltage ripple, on the output voltage ripple. Now the fourth problem was for totem pole PFC, which of the following statements are true? So the totem pole PFC uses diode bridge rectifier. No, because it is a bridgeless, it is a derivative of bridgeless PFC, so there is no diode bridge rectifier which is present at the first stage. Then at a time 3 semiconductor devices is in conduction. No, if you see in this totem pole, in this bridge only one switch will be on, and in the second half bridge it is only one switch will be on. So at a time only two switches are in conduction, so that is why this value is also not correct. Now then let us see the C. In this C, it is said that it is comprises of two fast switching switches and two slow switching switches. So if you look very carefully, in this one we have S1 S2 which is switching at a frequency equal to that of the switching frequency, which is FSW, while S3 and S4 is turned on only once in a line cycle. That means in positive half cycle S4 is on, in negative half cycle completely S4 is on, in negative half cycle completely S3 is on. So this S3 and S4 is a slow switching device, while S1 and S2 is a fast switching device. So that is why correct option is C. And fourth one, it helps in reducing the size of DC link capacitor. No, because it's a single phase PFC converter, and we have the second line harmonic ripple on the output voltage. So that is the reason why we we have to size our capacitance such that second line harmonic ripple will be as smaller, within the permissible limit of the load. So that is the reason why this D option is also not correct. Then for totem pole PFC, you have to obtain the duty ratio variation. for S2 switch, it is same as that of the it is same as that of the dt in positive half cycle, and it is 1 minus dt in negative half cycle. So that is why it is same as that of the dt in positive half cycle. 1 minus dt means you will get Vs peak by V naught, and that's why you will see the variation in negative half cycle going from, we have the same variation as that of sine omega t variation. While in the positive half cycle, it is 1 minus, it is just the d of t, that means it is 1 minus Vs sine omega t by V naught. So that's why we have 1 minus sine omega t, some constant time sine omega t variation comes into picture. So that's why it is of the variation something like this. So the correct option is D. Then in the sixth problem, it's straight from the slides, like how the transfer function gv of s looks like this. So again in this there are the correct answer is this one, which we have derived in the slide, which we have derived in the lecture. But there are some questions related to that, so let me clarify on those questions. So in this, what the questions what they have been asked is, if the the GV of S is V naught by IL, then how V naught S by IL of S, then how we will see a V naught value in the denominator. So this V naught value comes from the operating point, and this operating point is like a fixed nominal voltage for which the converter is been designed. So that is the difference between this operating point, and this is the small variation of voltage which is appearing on that. So that is the reason why we will have this V naught term over there, and we have also derived there. So you can understand how these expressions have been derived. Now one question was also asked in the mail that why while deriving the GI of S we have done average large signal model, then we have represented it in the state space representation, average state space representation. Then after that we have done the perturbation, and then after that we have linearized it by considering some approximations. So and then after that we have converted that into the S domain. So why there is so much of procedure one has to do while deriving for GI of S, while for deriving of GV of S, why the procedure is not so, what you can say, is not the same way. So the answer to that is simple, because if you look very carefully for GI of S, you have two modes of operation. Two modes of operation that happens during D of TS period, during D of T TS period, and 1 minus D of TS period. That means you have two different circuits which come into picture when you are at D of TS period and when you are 1 minus D of TS period. That means the voltage applied across inductors are different. So that is why the current which is being going through what you will get from the inductor, there is completely two different circuits. So what we have done there, we have take those two circuits and then we have done the averaging of that. The first step was averaging, and then only that we have so after that we obtain the average large signal model, and then we have given a small perturbation to those operating points. While if you see, while deriving the GV of S, what we are doing is we have this IL which is coming over here. This is my switches, and then I have this capacitor and resistor which has been there, RLC, and here I have my I converter. This is connected over here, and this is I have I converter, and this is my V naught. So what I am trying to do, I am trying to see how my V naught varies whenever there is a change in the I converter value. How there is, because see, the voltage across capacitor cannot rise suddenly or cannot change suddenly. It will respond to the change in the current through it with some delay, and that's why there is a dynamics corresponds to this. So now here if you see, it is continuous I converter which is going over there. There is no two different circuits which are coming into picture. So we do not have to do averaging. We have to just take the, we can directly define the S domain functions of that, and then we can just find out the expressions which will actually give you how how the I converter value gets linked with the V naught value. And this we and then we have already calculated how the I converter is connected with IL. So what we can do on an average sense, we have already understood how the IL will be, what you can say, will be can be represent how the I converter can be represented in the form of IL on an, you can say, on an average sense. So that's why we have then defined IL, I mean how the IL and V naught can be expressed. And finally what we are trying to see, we are trying to see whenever there is a change in the IL, how there is a how I mean with what response, or with what, how my voltage will respond to the change in the IL. So here this is just a single operating circuit which has been there. I converter is coming in parallel of RL and C. So we can just take the S domain equivalent of the impedance equivalent to this, and then take the parallel operation of that. So I mean parallel of RL and C. So we will get one impedance which is combination of parallel of RL and 1 by SC. And then so so we know that our whatever the voltage which is appearing is nothing but the whatever current which is coming over here multiplied by the impedance, and that is what we have done. And we have then represent I converter with respect in the form of IL, and that's why we get the expression V naught, V naught small signal divided by IL small signal, that transfer function. So that is the reason why this is the operating point we are talking about. This is not the, this is the small signal value. This is, however, this is the operating point which is at the nominal value. Suppose if I have given 400 volt, so that is the 400 volt which will come over here. However, this V naught is, we wanted to see whenever there is a small perturbation given to this IL, how the V naught will respond to that change. That means suddenly, let's say my RL get changed. Suddenly my RL gets changed. So IL will remain be the same, but RL gets changed. So you see that there is some voltage which is other than the nominal voltage or operating point voltage which you will see, and we wanted to capture that that particular voltage change. So that's why we have derived this particular expression. So these were the two questions which were quite prominent among the people. Again, there are again some more doubts which people have. Okay, same thing, the same questions which I have answered, why we have taken so much step to do that. This is the same thing which I think I have told now. Okay, sample problem related to assignment 5. Okay, we will see that in short time. And this, what is the common point between Vs and V converter? Okay, so this one, if you see this, how we define this, this is a single phase equivalent of our three phase three phase system. And when we define the single this single phase equivalent, what we will see is that there is a, the output of the half bridges will be nothing but a AC component. And I mean, again, this we are talking about with respect to the fictitious O point, while between the let me write down that. So if you see this one, I have, if I assume this is my fictitious O point, then I know that from this side what value I will get between VAO and 0 value, what I will get is nothing but AC quantity what I will get. And then this is connected over here with N point, with a neutral point here. And if you see between this neutral and this V between O point, what you will see, there is one DC component which is coming over here, which is called as the VNO voltage, which is called as the VNO voltage, which is the common mode voltage, which you will see. And this VNO voltage is nothing but equal to whatever the pole voltage which I will be applying from VAO, VBO plus VCO at a given instance of time divided by 3. that DC voltage will come into picture. And since we have taken, so if we try to see this particular circuit, it will look like you have a sinusoidal, then you have the, you know, a DC voltage, which is a kind of a common mode voltage which comes across N and O point. This is connected over here, this is connected over here, and this is connected over there. So between, so the circuit, if you try to see the single phase, this source is there. On another side we have inductor L, and there is L and RS which is coming to picture. So this L and RS which is coming into picture. On the other side, this is the VDC, the common mode voltage, which is always a DC value which you will get. And all on the other side, what you will get is, you know, your VAO voltage, which is V converter voltage, and this is my Vs of t voltage, and this is my common mode voltage which is up, which has been there. Now, since we have defined my fundamental component of the circuit, so that's why that is, and we are writing omega L, where omega is nothing but 2 pi fs. So that means we have defined my fundamental I mean single phase equivalent circuit in fundamental terms, fundamental harmonic term. So that's why all the other voltages other than this fundamental harmonic voltage, fundamental components will be zero if you apply just the superposition theorem. So that's why we will see we have the voltages, which is, we have the circuit which goes like this. We convert of t, and this is my nothing but RS, and this is omega L, and that is what we have written down. This is my, you know, Is of t, which is again in the fundamental component only. We are only of fundamental component terms only. So that is why my single phase equivalent, what you can say, my single phase equivalent circuit for the fundamental harmonic frequency will look like this, and that is what we have taken into consideration, and we have solved the entire what you can say, the all the expressions and equations. Okay, that is what I just wanted to say, and this again we can also take down this point. So this is just the L what we are getting. Yeah. So that was in the fundamental harmonic term what we were getting in the expressions, and then we started solving our circuit beyond that. So that was the answer to this particular question, question number 4. Now in question number 5, it is same question. It is being asked how the GV transfer function V naught will come in the denominator. So I'll just request the you know, let me also share the slide. I think it is in slide number 16. Yeah. So the same thing what I was telling, what we will do, we will just define my V naught voltage, whatever is coming over is nothing but the converter current which is going over there, and the parallel and the impedance which is appeared from the parallel combination of RL and C. So that is nothing but the impedance we have defined, and we have defined the I converter which is coming over here, and then we represent this I converter in the form of IL from this point, from this place. Here, because see, you know, whenever there is a change in the IL magnitude, it will directly get reflected in I converter, you know, this I converter magnitude, because the moment S2 is on, this IL is nothing but equal to I converter. So that is the reason why we have written IL in terms of, I converter in terms of IL, and that when we represent, so we will get Vs peak by V naught, and that is what we will get the expression V naught of S divided by IL of S is nothing but Vs peak by 2 V naught. Again, these are the operating point values. So the operating point value means, let me, if I give nominal voltage as 400 volt, it is a 400 volt. If it is given 230 volt RMS, then it is 325 325 by 2. That would be my operating point values, point values, and these are all RS, CS, all those things will be there. So that is how you can, these are all the questions which have been asked. Now let me see, or let me discuss some of the, let me discuss some of the problems, some of the hints how you can solve this problem for assignment number 5. Okay. So, some of the problems are straight. Just you have to figure it out, the things. So, let me solve one problem where, for example, let us take our flyback based PFC. So the circuit is something nothing but looking like this. And after that my PFC converter is there. Assume this is my PFC which is been connected. As my switch is there, and this is the unity which is coming over there. Time comes over there, and then C and RL. Sorry, one mistake I did. I dot in the other direction. Okay. Now we know that we have already solved in our this one, which is the duty ratio of this S1 switch will be nothing but 1 by 1 plus VSP minus sine omega t by V naught. That is the value what we have given. And let's say if someone have asked for the positive, positive peak, so that means my omega t is nothing but 90 degree. That implies my duty ratio is nothing but 1 by 1 plus Vs peak by V naught. And let's say if someone has given your input voltage rating, so that will be obviously in terms of RMS value. You can just calculate the okay, we have missed one term which is the N term. So it was in the lecture number. Okay, sorry, I missed one term which is N V naught. So which is here it was N, and where N is nothing but we have defined N as, let me see, N we have defined as N raised to 1 in this way. N raised to 1. We have defined N raised to 1. So that is the N. So here also N will come. So you have all the data. If everyone, if they have provided the V naught value, let's say if in the question the V naught value has been provided, the input voltage has been provided, and N has been provided, you can easily calculate your duty ratio values, following this equation. Then if someone, there is also some question where we know that our our L value for which is the per phase inductance value for three phase system, three phase AC/DC converter, we have already derived in the lectures, which is three phase AC/DC converter, which is nothing but L under root M V naught by 2 square minus Vs peak square divided by 2 by Fs Is peak square, that we have already derived. So when we see in this one, this Vs peak, if in the question, if they have provided the voltage input given, so that is known. V naught, if they have given in the question output voltage, that is also given. Fs is nothing but your supply frequency, generally with the input information there, that formula is also been given. Now you have to calculate Is peak. So if in the question, let's say if it is given that output power is, let's say if it is given, let's say PL, load power, so it is nothing but Is peak will be nothing but PL divided by, and if they have given the three phase voltage, let's say whatever voltage they have been given, that will be V line to line RMS, that will be the voltage. So our power in so we, what we can do is we will do the power balance, and that is when we can do power balance. I mean, we consider it is a lossless converter if there is no efficiency term is being given. So power balance we will do, where we will make P in equal to P naught, and that is when we will get P in equal to PL, and that is when we know that our input power is nothing but, it's a three phase system, it is nothing but 3 times P phase RMS multiplied by I, Is, or you can say I phase RMS, and cos phi is 1 because it's a unity power factor operation. Generally if it is there, then it is cos phi is equals to 1. So what we will do is, in this particular case, our we wanted to calculate Is peak, where Is peak is nothing but peak of phase current. So what you have to do, you have to just, from here we can just write down, so from here if we see in this from equation number 1, if we derive, if we see, what we have is I phase RMS is nothing but PL by 3 into V phase RMS, and this, if you try to solve this particular thing, so I phase RMS will be nothing but PL by 3 into V phase RMS. Now we know that our mostly our systems are star connected system, so V phase is nothing but equal to whatever line to line divided by root 3. So you will just do V line to line RMS divided by root 3. Here if you do divided by root 3, so it will become root 3, and that is when what you will get is V phase RMS, V line to line RMS, which is if it is given for three phase system, it is the line to line RMS value which is being given. So this is what you will get, the RMS value. This multiplied by root 2 will give you the I phase peak, which is nothing but equal to your Is peak value in the in our discussions what we have taken. So by this way you can simply calculate Is peak, and once you calculate Is peak, you put it in this formula, you will directly get the inductance. Similarly, if the inductance is been given and all the other values has been given, you can back calculate and do the rearrangement and calculate the M value. So that is how you can if this kind of questions is been given, you can solve. Then if in the question it is given, if in the question if it is given that the fundamental, the peak value of fundamental component of output of half bridges, we know that it is nothing but, which is nothing but VAO, we have already derived in our, or we have already shown in our lecture, is nothing but if we see our VAO average value, what is the VAO average value? It is M VDC by 2 sine omega t. That is what we have obtained. So if you see in this one, so what it indicates? It indicates that the peak of the fundamental component of output pole voltage of half bridge is nothing but MVDC by 2. So it is nothing but MVDC by 2. So from MVDC by 2, that is what we have reached to MVDC by 2, and from there we can easily calculate VDC is nothing but our output voltage what we are getting. So from there we can easily calculate, if in case of half bridge VDC is nothing but the your this is the half bridge, this is the VDC which I'm talking about. This is, let's say this is A, this is fictitious O point, this is VDC by 2, and this is VDC by 2, and this is my load L and R which was this. So you can easily calculate once you know the peak value of that, and if let's say if you know the DC link, you can calculate the modulation index, and once you know the modulation index, you can use that modulation index to calculate if in the question different RMS values are been asked, so you can use this expression to derive the modulation index value. So using this you can calculate M value. So I think that is what I think these are some of the hints you can use to practically try to solve the assignment number 5. Any further questions you have you wanted to ask? I think if no questions are been there, let me stop for today, and we will meet in the next live session which will happen uh, probably on next Saturday, or if not then maybe week after that. Any questions? I think no questions. So let me stop for today.